So, today, two main things we're going to focus on. One is chapter 3 homes. Our third assignment I'm going to collect today. Do you guys have any questions about any of the things on that particular assignment?
For 21, I got 1.44 times 10 to the negative 73rd.
Negative 73rd.
Yeah.
Interesting. What about your other answer?
I got 5.93
Okay.
times 10 to the negative 74.
Ah.
So I don't know if it
Huh. I suspect that might be due to if you put, like, say, if you try to combine multiple lines into the calculator at once, it could be that it didn't combine some of these terms correctly. Like if, say, one of these numbers got squared in a weird way, or added, subtracted, divided in a weird way, I could see that happening. I would have to look at your work specifically to see what might have happened, but I suspect it's entirely the calculator's fault. For a sense of scale, 21 is about balancing the electrical forces between charged particles. You've got an electron here, a proton here, something else in the middle. How far apart do they need to be to balance? So these numbers we're solving for are physical distances. If the answer was that tiny, the particles would basically be overlapped inside of each other. Which, again, we can find that number, it just doesn't make any physical sense. I am entirely blaming your calculator. If you have work, I would happily look at it, but I do think it's the calculator's fault. And this is why I tend to, we've talked about and done samples of putting everything into the calculator at once. I very rarely actually do that in my own work. I tend to simplify one line at a time, or at the very least, one line at a time in the calculator. When I was reworking this today, I wrote this up, and within my calculator found each of these combined forms separately. Then, when it came time to this one, I, without the square root, subtracted these two terms from each other, and then took the square root of the answer. I tend to take things into as many different lines as needed so as to avoid exponent getting left out or lumped in a weird way. I would expect if you did it again, you would get answers more closer to these. And your numbers are fine. The problem is that weird exponent on the end. Like the numbers you described match this. The problem is something along the way added that times 10 to it in there. So it's okay if I am fine collecting this assignment on your way out. If you would like a second to rework it, check your calculator again. I don't mind looking at it with you as well. Is there any issues you found? Okay. This is the pile of assignments being turned in. So just make sure that your work is in this pile before you go today. As for what we're going to be doing for the rest of this week, this is the new assignment. If you were looking at, I've started uploading the assignment files to Brightspace, and I did complain to Brightspace Manager. He says you should be in now. Okay, very good. I'm planning on uploading all the files directly to it so that people can work from a digital copy if they don't want to have to keep track of a paper one. That said, if either of you have looked at that particular draft of the fourth homework, I have re-looked at it, reorganized what I want to prioritize teaching when, And I've basically rebuilt the assignment, cut some things out, added some things in. So that particular assignment is, I'll be changing the file shortly. If you looked at it and started on it, some of the questions are the same, but I've changed a few things to make it easier and more intuitive for students. So this paper copy up here is the correct version, and I'll be changing the file to match accordingly. And what we're going to be focusing on this week is geometry, trigonometry, and Pythagorean type math. Talk briefly about the upcoming calendar. This week, we're going to be focused entirely on this particular assignment. Today and Friday, we will be looking at samples, working problems together involving these particular topics. And I'm going to try to be tying them into physics examples that you will commonly see at the beginning of 100. Next week, I'll collect the assignment on Wednesday, as per usual, and we will spend Wednesday reviewing that and everything else that we've done. And I'm going to move the test to next Friday. That way we'll have time. I'll have time to grade everything for you guys, and we'll have Wednesday to talk and plan and study. So, our first test will be next Friday, not next Wednesday. We'll just be here in class together. When you get the paper copy, I'll be here to answer your questions, and I'll just have it by the end of the period. And after that point, we'll move on to the next batch of lessons. And then we'll have, sorry, I don't think too far ahead. And so that's the next week in life class. Now, when I say trigonometry and geometry, when I was in high school, those classes meant and were about, shapes and triangles and SOHCAHTOA and all that. I very recently was a high school teacher. I taught high school physics for a little while. And while I was there, my students would complain about their trigonometry and geometry classes. And they're allowed to. I like them, but not everyone does. But when I asked what about it they didn't like, they started complaining about proofs and derivations and integrals and things like that, which isn't geometry or trigonometry at all as far as I'm concerned. I think somewhere along the lines after I finished high school, some school system might have changed what things are called for some reason. So if at any point you had a class with a name like that and you were dealing with proofs, that's not what we're going to be doing in here. That's not going to be what's coming up in physics either. This is triangles. It's something that's always confused me ever since that last job. I just never understood why they do that. So I just wanted to reassure all of my classes in case anyone has dealt with something similar. So, any questions before we begin diving into these categories? Okay. Now, triangles. I can turn most physics questions into some combination of triangles. They are unavoidable. The reason for this is we live in a three-dimensional, at least in terms of physical space, we live in a three-dimensional world. Any 2 points can be distinguished from each other based on their x-coordinate, their y-coordinate, and eventually you can expand into the depth of the z-axis as well. So we have x, y, and z. That's 3 dimensions, which forms some nice symmetry with the 3 sides of a triangle. But what's important is all of these dimensions are perpendicular from one another. All of these axes form right angles with all of the other axes. Because of that, right triangles show up everywhere in nature. You might not always see them physically, because any vector can probably be broken down into a right triangle. This includes things that you can see, like distance and length, but also things like velocity, acceleration, and force. So the triangles are going to form the backbone of a lot of that, at least for two-dimensional motion and eventually three-dimensional motion as well. Now in physics 1500, 1510, we're not going to look at much 3D. We're going to stick mostly to 2D, because 3D becomes a lot more complicated. So this can be considered your start, or rather your reacclimation to two-dimensional physics. So, to describe a very common physics situation where this shows up, and one more questions as well. Let's look at this tree. It's a sunny day. You can see the sunlight, and please do stop me if you've seen this type of question before. It is rather hard, at least in my experience, to measure the height of a tree if I'm just a person with a tape measure. Because knowing my luck, the tape measure will fall over. Knowing my luck, the tree will fall over. So, rather hard for one person by themselves to just figure out what the height of the tree is. What you can usually measure across the horizontal ground is the length of the tree's shadow. So, we're assuming, in this situation, the tree's vertical height is at a right angle to the horizontal shadow cast along the ground. And because they are at a right angle to one another, we can draw a right triangle. And this angle is the right angle. The other two angles depend on the thing that casts the shadow, which in this case is the light of the sun. So we're going to commonly use Greek letter theta to represent angles. I will usually draw it on a triangle to show what corner we are specifically looking at things from the perspective of. And then I will reference that within the formulas. So if you were just a person with a tape measure and a protractor, you could measure the angle between the ground and wherever the sun is at that moment casting the shadow. With that information, we can measure shadow length and this angle. We can draw out this right triangle and figure out the height of the tree without ever having to actually climb it. You guys done a problem like this before, I presume? Okay. Yeah, this is okay. This is entirely reflector. So, on your calculators, they should have on the faceplate sine, cosine, and tangent buttons. Sine, cosine, and tangent form the three most basic trigonometric functions. And they are operators like square root and square root. You perform it on something and it gives you a new answer. They do have longer drawn out formulas, but when I looked into what they were, they are very complicated and they literally go on infinitely because there's a factorial in them, which is why we usually just automate it to our calculator, because I don't want to work an infinite equation. I don't even want to work it to the 10th place. So we, by and large, have just outsourced that task to our calculator wholesale. So we have on the faceplate the sine, cosine, tangent buttons, and we have a very, very common mnemonic to remind us how to use each one. Each part of the mnemonic reminds us how to use one piece of sine, cosine, or tangent. And I don't know why, but in my head, SOHCAHTOA always ends up sounding more like a battle cry than a mine. But I don't know what math department would be at war with someone else. So brief refresher. Sine opposite hypotenuse. I prefer writing them out like this, but remembering so helps remind me what to put where. So I'll usually write it out both ways. Sine operator applied to any angle will tell you the opposite leg from that angle divided by the hypotenuse of the triangle that angle is in. So looking at our brief tree sample here, if this is the angle that we're using as our base, because this is the one you could measure with a protractor to the sun, the opposite leg from this one is always the one that isn't touching it. Meanwhile, the hypotenuse is always the slanted one. So, if we perform the sine operator on this angle, we will get whatever fraction is formed by dividing opposite over hypotenuse. Say, for example, this angle was 15 degrees. We could do sine of 15 degrees, and that would give us 0.26. If we knew one or the other opposite or hypotenuse, we could use this statement to find the other one. That said, for this tree situation, does so help us find tree height? Sorry? Yeah? So, that was a pun. So, sine equals opposite over hypotenuse. We could, if we knew what the angle was, we could get to a point like this. Can we solve this for the height of the tree, which would be the opposite leg in the situation? If we've only measured the shadow length, almost. If we only know shadow length and don't know hypotenuse, this can't tell us opposite yet. So if we look at the next couple ones, CAF, cosine of an angle equals the adjacent leg over the hypotenuse. The adjacent leg is the non-hypotenuse leg that is touching the angle in question. And this doesn't have the leg we're looking for in it at all. Because if this is our starting angle, the tree height is the opposite from that. So this can't tell us opposite at all. Now, we could use this to find hypotenuse, and we could then plug hypotenuse in here to find opposite. So they form a nice sort of two-punch system. But tangent takes those two and combines them. So the last term, TOA, tangent of any angle will equal the opposite leg over the adjacent leg. In this situation, we could measure this angle, we could measure shadow length, we want opposite. So for this situation specifically, we would turn our attention to the tangent function. And this is very similar to the first question on the assignment. So we're going to start plugging those numbers in. We are told the shadow length on this particular tree-sun shadow combination is 10 meters. And that the angle in question is 15 degrees. So, we know our angle, we know adjacent, and we want opposite. The function that contains all of those is TOA, tangent of theta equals opposite over adjacent. Plug in what we know, tangent of 15 degrees is equal to the opposite leg over our adjacent leg. And we can solve for that opposite. Now, when doing this, calculator is a wonderful tool because, again, you never want to have to do the sine formula by the sine, cosine, or tangent formula by hand. It's the worst. I've never actually done it myself all the way drawn out because it's terrible, and I have this instead. The problem is, you can either plug in degrees or you can plug in radians. Radians is basically just a different measurement for degrees, kind of like how feet and meters measure the same thing, just a different metric. And because they both measure the same thing, and because they're commonly used as different units for the same thing based on whether or not you're a mathematician or a physicist, the calculator has been designed to be able to handle both of them, but it can only handle one of them at a time. When I type tangent of 15 degrees into my calculator, it gives me 0.2679. Do either of your calculators not give you 0.2679? I'll actually write that up there because it's in this line. Did you both get 0.2679? Okay, very good. That means your calculator is in degrees mode at this very moment, which is good because we plugged degrees in. We will be looking at radians in this particular assignment. So, as a refresher again, it's just another unit for the same thing that degrees measures. It's just another way of measuring angle. And I'm going to put the unit circle over here in the corner because that was a unit circle question on your assignment. I'm going to help you fill in a few of the blanks to start with. We always start these circles from here at the x-axis. So that's 0 in all scales, 0 degrees, 0 radians. Up here, if we're going counterclockwise, up top we would have 90 degrees, which is the same as pi over 2 radians. I'm going to abbreviate that commonly as rad. So 90 degrees is equal to pi over 2 radians. We can come over here. The next chunk would be 180 degrees, which would be pi radians. So a whole pi worth of radians, 3.14 radians. Next, 270 degrees would be 3 over 2 pi radians. And if we lapped all the way around to the start, 360 degrees would be 2 pi radians. So, the conversion, which I recommend you have written somewhere in your notes, 180 degrees is equal to pi radians. Really, you can use any of these as a conversion, but I like this one though because the pi comes out as a, well, at least a whole, that fraction of pi instead of a fraction. You could also use the 360 equals 2 pi radians. And they measure the same thing, it's just a question of what setting your calculator is currently tuned to. To prove that they mean the same thing, we can do tangent of 90 degrees, and that yells at me because you can't actually do that. Let's do tangent of 45 degrees. All right, so I've got tangent of 45 in there. And in degrees mode, it gives me 1, which is correct. You're already in degrees mode, which you will need to be in for most of this particular assignment. That's fine. But to go ahead and show you how to swap them, if you haven't done this in a while, on mine, if you hit the mode button, it brings up a menu of a lot of different modes of operation you can be in. For me, the third option is either radians mode or degrees mode. If you hit select on radians, that'll put you in radians mode instead of degrees. And if I do tangent of 45 again, it gives me a different answer. Because now instead of 45 degrees, it's looking at 45 radians. If I instead do tangent of pi divided by 4, which would be the same thing as 45 degrees, it gives me 1 again. So do remember how to switch between the modes, because that will come up a lot here and in most other classes in this department. I'm going to switch mine back real quick. So just mode, and then select whether or not you want to be in radians. While we're still kind of looking at the unit circle, on the unit circle in your homework, these ones in the middle, you got 45 degrees, you got 30 degrees, you got 60 degrees. And the other quadrants have them at the same intervals. So the middle one on this quadrant would be halfway between 180 and 90, and the other two would be 30 from one side and then 30 from there. So just to go ahead and give you a leg up on that. So to look back at the original sample question, we make sure we're in degrees mode. Tangent of 15 degrees, it should give us 0.2679. That's equal to the opposite divided by 10. If we simply multiply 10 to both sides, that should tell us this particular tree is about 2.679 meters tall. Questions so far? Okay. So that is basic direct application of where this would show up in physics, and also just a useful trick sometimes. I'm sure there will be a point at some point in your life you'll need to measure the height of something improbable. The second question on the assignment is very, very similar to the first one, except it's a little bit of an actual homework project, because for number 2, I'm asking you guys to actually go to Bluehenge, which at least in my day was the name of the weird series of pillars next to Smith Admin Building. They still call it that? Okay. Granted, this will have to happen on a sunny day, but on a day where you can see the sun, go there, measure the shadow. You can estimate what the sun angle is. I do recommend having a protractor, but measure the shadow length, estimate the sun angle, give me an approximation of how tall the pillars are. I like the pillars for this because it's a lot easier to define the end of the shadow of a pillar than it is to define the end of the shadow of a bushy tree that has a lot of negative space in it. Now, on the first page, the rest of the questions give you various triangles that you then will figure out all of the dimensions. What that means is all the side lengths and all of the angles. So one of the reasons I made them a little bit larger and take up some more space is so that you have a little room for work, but also room to physically write everything on all the triangles. Let's take a quick look at one of those so that we can also remind ourselves how to use inverse sine, cosine, tangent. So number 2 is we go measure a pillar. Number 3 gives us a new triangle to look at. We are told right off the bat the lower left leg is 57 degrees and the bottom leg is 5 inches. We can also tell that this is the right angle, so that leaves us with 1 mystery angle and 2 mystery sides. I call this leg A, so that leaves us with B, C, and other angle. You know what? I won't call that theta. Just put a question mark. So, I want to talk about the other intro tips and tactics, just to get them back into your head, that one can use on these types of questions. I like having all of the angles to start with. So let's talk about a common trick to find the remaining angles. So trick 1. Okay, SOHCAHTOA might be trick 1, but this is trick the next. Remember that all the angles in a triangle add up to 180 degrees. So for this specific triangle, we already know 2 of them, because the right angle is always 90 degrees. So all the angles add up to 180. That means that 57 plus 90 plus whatever that third one is has to be 180. We can work back to find the mystery angle without even having to do any actual trigonometric functions. So it's a basic geometry fact, but it's one that never stops being useful. That would give us, for our mystery angle, 33 degrees. Trick number 2. Remember how to do inverse trig. This is more of a calculator function. Let's say that our next goal is to find leg B. this very similar to the other question. Well, you know what? Let me back up just a little bit. Let's go ahead and find B really quickly, because I need B to actually show the other tricks. To find B, we know this leg, we know either of these angles. I'm going to stick with the 57 now. So angle, opposite, adjacent, let's use tangent again. Tangent of 57 degrees will give us B over 5. That's giving me 7.699 inches. Does anyone disagree? Okay. So B is now known, which is very handy. Now that we have B, I am going to refresh your memories on inverse trig. We already found our mystery angle, but let's pretend for just a second that we haven't. Let's say that we want to find our mystery angle. And we aren't using this trick for some reason. Let's say we want to find it some other way, or we have to find it some other way. Say we don't know any of the angles. This is our mystery angle. From this perspective, A is the opposite, B is the adjacent. We know both of these, so we can use tangent. Tangent of our mystery angle, so opposite, so 5 over 7. Call it 7.7. How do we get question mark by itself? Almost. We do need to cancel it out, but tangent is an operator kind of like a square root. Yes, so we need to do the inverse of tangent, like how the inverse of a square root is the square. And this is a different button on your calculator. So kind of like how square root and square root cancel, or natural log and raised to the e power cancel out. Tangent is canceled out by tangent's inverse, which is literally called inverse tangent. So we need to perform the inverse tangent operator on both sides. This is its own unique operation, and as long as we do it to both sides, this is legal. When you take the inverse tangent of a tangent, the two tangents cancel, and you're just left with whatever was in the tangent. So the left side would just now become a question mark. And that would leave us with inverse tangent of 5 over 7.7, which is all well and good until you need to get your calculator to actually give you that number. So when you look at your calculator, at least on mine, the inverse tangent function is the secondary function of the tangent button itself. So if you hit second tangent, now it's tan to the -1 power of blank. Put in 5 divided by 7.699. And that gives us exactly the answer you would expect, since we already found this angle, 33 degrees. So we've proved that both these methods work. They both gave us the same correct answer. All trig functions have inverses. And if you look at the buttons, there's also an inverse sine above sine and an inverse cosine above the cosine. You can cancel any of them in the same way. And you can also undo an inverse tangent by doing tangent upon it. So the situation works in reverse as well. So trig 2, remember your inverse trig. Trig 3 is an oldie but a goodie. I don't even think it's a trick technically. Everyone's favorite, the Pythagorean theorem. What's the formula? Very good. So the sum of the two legs squared is the hypotenuse squared. The only real difficult part of this to remember is z is always the hypotenuse. So 2 legs, hypotenuse, and make sure to square each term before you add them and start moving them around. Looking at what we've got here, of our 2 non-hypotenuse legs, we have 5 and 7.7. So 5 squared plus 7.7 squared equals c squared. And 25 plus 59.27 equals c squared. Square root of both sides. And I've got 9.18 equals C. And to prove that this works, you can also find this number using any of these. Oh, okay. You can't find hypotenuse with tangent, but sine and cosine can always tell you hypotenuse. So we can use these functions also to find the same hypotenuse. There's a lot of different combinations of ways and steps to work all of the triangles on this assignment. There is not necessarily a guaranteed method for, you have to do it in this particular order. If you don't like the Pythagorean theorem, you can set it up to where you never have to actually do it. You can use the other tricks instead. I like the Pythagorean theorem, so I usually try to work it so I do end up on that step. But you don't have to if you don't want to. Any of these can be avoided. We are nearing the end of the period. I don't want to keep you long today. Next time, we will look at the slightly more complicated triangles. There are 2 on here that aren't directly right triangles, but I can show you how to make right triangles out of them, which is my preferred tactic. On the second page, we're also going to look at the 3 other trig functions. In addition to sine, cosine, tangent, we also have cotangent, secant, and cosecant. They're not much harder, but I want to just start off with these for now, just as a refresher. And be working on these, looking at these. I'll go ahead and actually show you what I would do on those combo triangles. Oh, that's where that went. Just if you want to get started on them. On the second page, 7 and 18 by themselves aren't right triangles, but if I do this and this, Suddenly they're made of 2 right triangles each. So, be working on those. We'll address questions and work some more together on Friday. Let me know if you encounter any issues looking at these. And do have a wonderful day. You don't have any questions now.